Today we will be building a gravity simulation in Python. Let's start by creating a body. Here we will give our body class certain parameters, including its position in the x and y plane, its velocity, some mass and a diameter. We will also create this radius attribute. This will be used in rendering the body. And lastly, we will create this list of previous locations. This can be used in rendering a trail for the body later. And if we click on the screen, we can now create our body. Excellent. We now need to consider how we are going to make the body move. Unfortunately for us, it is impossible to calculate the exact movement when there are more than 2 gravitational forces acting on the body. This is known as the 3-body problem and has no exact solution for all arrangements of bodies. However, it is possible to approximate motion through the use of numerical methods. One such method is known as Euler's method, which is the simplest of the numerical methods. Unfortunately, this also means it is the least accurate. However, it is the most computationally cheap. This means we will be able to support a larger number of bodies than we would have been able to should we have chosen a different method. Let's consider the velocity on a graph with respect to time. The actual shape of this graph is entirely arbitrary, but let's consider it looks something like this. Euler's method works in what are known as time steps, so every time step corresponds to a new frame in our simulation. Here's the formula for the Euler method. The velocity of the new time step is equal to the velocity of the last time step plus the acceleration, multiplied by this h here, which corresponds to the length of a single time step. We can see here that we simply draw the tangent of the last time step, and where that intersects the new time step will be our new point. We can also use the same method with position, and instead of multiplying the length of a time step by the acceleration, we simply multiply it by the velocity. You can see that in some cases the points don't exactly line up with the real function. This is due to the fact we're only using a tangent of the previous time step. However, the accuracy can be improved by decreasing the length of a time step. Here, the time step is a single second. However, in our simulation, we can decrease it to something smaller, like 0.2 seconds. Here we will write 2 methods for our body class. We'll also include this universe time step variable. This refers to the length of a single time step. Here we'll add a method to update the velocity, and here we'll add one to update the position. Let's give it a run. And here we can see our body now moves to the right with a constant velocity. The body should also be affected by acceleration, but we'll demonstrate that in a moment. Let's consider Newton's universal law of gravitation. This law tells us the magnitude of the force between 2 bodies. When the bodies are far apart, the force is very weak, but when the bodies are closer, the force increases. However, this only tells us the magnitude of the force acting on a single body. What about the direction? We will write the direction as its own vector. This represents the direction of a force acting on the body. If we resolve this vector with its x and y components, we can see that it looks something like this. Our x and y components are now written as separate vectors. Now, let's normalize our direction vector. This means to give it a magnitude of 1, and we'll use this d hat symbol to represent the normalized vector. We can now find the force vector acting on the body by combining the magnitude with the normalized direction vector. And here it is. This tells us the force acting on a body. The top row represents the x direction, and the bottom row represents the y direction. If we combine this equation with Newton's second law, we can create an algorithm for calculating the acceleration. Combine this with Euler's method and we can know how a body will move at any given moment of time. Let's create a new method to handle this new behavior. We'll have this update method under our body class, and we'll start by looping through every other body in the list. If the body is not the body we are talking about, we will implement the equations we showed earlier. This is to avoid any dividing by 0 errors. We will then add the individual force to a resultant force, and they will then implement Newton's second law. We can then apply Euler's method to calculate the change in position and change in velocity. I also added a trail so you can see where the body has previously been. I did this by creating an array of all previous body locations and drawing a grey dot where the bodies were previously. But we can do better. Let's add a little bit of colour.